Hey guys, in this video we're going to learn about how to actually calculate the magnetic field due to a wire or two wires or I don't know, any number you like, I suppose, but usually one or two different wires. Now, the equation that you're going to use is this one right here. Most of these variables you probably already know, like, there's some constants there. Great, cool. All right, and then R is going to be the distance of a particular point from the wire, such as the point where you want to find the field. And then I, of course, is the amount of current going through the wire. So based on sort of the shape of this equation here, you can see that a greater current produces a bigger magnetic field, and at a greater distance, the field is weaker. So here, close to the wire, the field is stronger. Here, further away from the wire, the field would be, say, a little bit weaker. And then, of course, very far away, the field is very weak. There is one thing in here that you've probably never seen before, however, and that is mu naught. It has nothing to do with friction. That's called the vacuum permeability or magnetic permeability, and it has a value of 4 pi times 10 to the negative 7th. So if you like, this equation kind of turns into, I mean, you got a pi on top and bottom and also a factor of 2. Okay, so I'm not saying that the value of mu naught is actually 2 times 10 to the negative 7th, just that this equation would simplify to every single time 2 times 10 to the negative 7th times I over R. So every time, that's actually what that equation is going to simplify into. If you're wondering, why didn't they just write it like that in the first place? Well, we physicists have our reasons, which will become obvious in maybe some other equation having to do with magnetic fields. But whatever, it's just going to be this every single time. Now, reminder for these problems, everywhere to the left of that wire, the field would be out of the page. Everywhere to the right, the field would be into the page, and that's based on the direction that current is moving. And I can again verify this result using the right-hand rule, right? My thumb is pointing up the page, the direction the current's flowing, and my fingers are pointing very clearly out of the page towards you. So that means that to the left of that wire, since my hand is pointing to the left, the field's going to be out of the page. Off to the right, got to turn my hand around here, the current would be, again, my thumb. My hand is pointing in that's sort of my radial vector, right? Which side of the wire am I looking at? So off to the right of it, my fingers are pointing into the page. As expected, physics wouldn't really be physics without, say, like, I don't know, something more complicated like 2 wires. 1 wire. That's so tame. So of course we have to have 2. And also, to make matters worse, probably they're going to have different currents running through them. I mean, there's no reason they have to be different. They could be the same. But in this scenario, right, we've got one current up the page, one down the page, and we're supposed to find the magnetic field at these 3 different positions. Well, I wonder what steps we should take here. Let's do these steps. Step 1 is draw each of those magnetic fields. All right. Then we can go ahead and calculate. And then after we've calculated each of those individual magnetic fields, we'll decide whether we're going to add or subtract based on what we did up here in step 1. So here is me beginning step 1. Off to the left of wire number 1, which every field produced by that one I'm drawing in blue, you will notice. All right, off to the left of it, we have a field going out of the page. That's all these blue dots over here. To the right of it, the field is going into the page. That's all these blue X's. And that applies also over here, you will notice. So it's not like wire number 1 doesn't affect the magnetic field, say, off here, just because wire number 2 is, in the way or something. It's producing a magnetic field everywhere around it, off to the left, off to the right, as far away as you want to talk about. And so I need to continue drawing my dots or X's on sort of both sides of each of the wires for the fields produced by each of the wires. All right, let's draw the one from I2 now. And this is what we get. So notice in this region, we've got dots and X's. One wire makes dots, one makes X's. So that means that the fields are in opposite directions. We could say the same thing over here. One wire is making dots, the other is making X's. So those fields are going in opposite directions. In this middle region, though, the fields agree. They are pointing in the same direction. And so based on the agreement or disagreement of those dots versus X's, we can see that everywhere off to the left of wire 1, the fields will subtract. Same idea for to the right of wire 2, and in between the two wires, that's where the fields are going to add together. The next step is we have to calculate each of the magnetic fields at that position. Meaning each wire, as we've said, produces its own magnetic field at that point. We've got to calculate both of them. So the magnetic field produced by wire number 1 relates to current number 1. And also, really I should have said 2 pi r1, because wire number 1 is that far away from point 1, whereas wire number 2 is this far away. All right, now based on the distances I've labeled down below here, I shouldn't have too much trouble figuring out what R1 and R2 are, with the usual caveat that you have to make sure not to plug in centimeters directly. So meters, please. Okay, now if I plug in my values, I should now be able to calculate each of the magnetic fields, and I will get tiny, tiny little numbers, guys, tiny numbers. Teslas are, well, remember 1 Tesla is pretty big. These magnetic fields would absolutely be enough to say like divert a compass needle, but it's not going to be enough that you're going to be able to, I don't know, stick a piece of iron to it or something. Fine, so we've got 8 times 10 to the negative 6th and 4 times 10 to the negative 6th. Now to get the total field at that point, that's where we have to think back to what we had on a previous slide. Do I add or subtract? That's right, we subtract, and so we get, boom. All right, I like it. Now, for the other 2 points, honestly, the process at this point is kind of repetitive. So what I'm going to do is I'm just going to pause for like 3 seconds with a little bit of work and then move on. So you should work out those 2 points on your own, or say work out 2 and then pause and see if you got it right, and then try out 3 and repeat, okay? So do them and then watch the rest of my work. Starting now. Alright, that's all. Thanks for watching, guys.